Have you ever wondered how AI can diagnose diseases from medical images? It's like magic, feed it a scan, and suddenly it knows if something's wrong. But here's the tricky part. Most AI models are like black boxes. They give answers, but we don't always know why. That's a big deal in medicine, where even small mistakes can have huge consequences. Enter Concept Bottleneck Models, CBMs. Think of them as AI's way of explaining its thinking. Instead of just saying cancer, a CBM might say, the model thinks this is cancer because it sees irregular cell shapes and dark spots, features we know are linked to this disease. But here's the problem. Most CBMs only look at the last layer of their visual processing. Like relying on a single doctor's opinion instead of a team. What if I told you that different layers in an AI's brain focus on different things? Some might spot textures, others shapes, and others still abstract patterns. Researchers discovered that concepts, like irregular cell shapes, are better recognized by different layers of the model. But traditional CBMs ignore this, sticking to the final layer and missing out on the bigger picture. That's where MVP-CBM comes in. It's like giving the AI a team of specialists. 2 key ideas. 1. Intra-layer preference modeling. It learns which concepts each layer is best at recognizing. 2. Multi-layer fusion. It combines insights from all layers, like a committee of doctors, to make smarter, more explainable decisions. The results: MVP-CBM outperforms existing models in both accuracy and clarity. It's not just faster, it's more transparent. For example, in skin cancer detection, it might highlight that layer 7 spots a strawberry pattern, while layer 11 notices glomerular vessels, both critical clues. And here's the kicker: it reduces reliance on manual labeling. Instead of humans painstakingly tagging every concept, the model learns which features matter most. Imagine you're trying to diagnose a medical condition using a deep learning model. The model looks at images, like skin lesions or X-rays, but how does it decide what to focus on? That's where concepts like concept activation scores come in. These scores highlight which parts of an image are most relevant to a diagnosis. But here's the challenge. Modern models often process too many tiny visual details, making it hard to spot the truly important ones. So how do we fix this? Let's break it down. First, the model identifies key diagnostic attributes, like the color, texture, or shape of a lesion. For each of these attributes, it pulls the most relevant features from different layers of the network. Think of it like filtering out noise. Instead of looking at every pixel, we focus on the details that matter most for each specific clue. But even then, some features are more important than others. That's where attribute preferences step in. The model adjusts activation scores based on how strongly each feature relates to a particular diagnostic attribute. If a feature strongly ties to a key symptom, it gets amplified, like turning up the volume on the most critical clues. Now here's the smart part. Not all layers of the network contribute equally. Some are more useful than others. To streamline things, the model sparsifies less relevant layers. It's like decluttering a room, removing the stuff that doesn't help you find what you're looking for. By applying a thresholding mechanism, the model zeroes in on the most impactful layers, reducing redundancy and boosting reliability. Finally, all these adjusted scores are aggregated into a single, concise representation. This fused activation score isn't just accurate, it's interpretable. The model doesn't just guess, it highlights why it's making a decision. So next time you hear about AI in medicine, remember, the future isn't just about smarter algorithms. It's about explainable ones. Models that don't just diagnose, but tell us why. That's the power of MVP-CBM, and it's just the beginning.